Welcome to your AP Statistics Chapter 19 lesson on confidence intervals for proportions. This is Mrs. Brown, and I'm here with Daisy and Scout, and we are ready to talk about statistics. Okay, standard error. Both of the sampling distributions we've looked at are normal. So for proportion, the standard deviation is of p hat. The sampling distribution of all the sample proportion is equal to the square root of p times q over n, where p is the population proportion. The standard deviation for sample means the sampling distribution of all the sample means for a fixed size n is going to equal the standard deviation, the true standard deviation of the entire population of x's divided by the square root of n. Okay, we're really focusing in on proportions, so let's look at that case. Here's the deal. We usually don't know p, and when we're working with means, we don't know sigma, so sometimes it seems like maybe we might be stuck, but we're not. We will use sample statistics to estimate these population parameters, and when we do that, the estimated standard deviation is called the standard error. For a sample proportion, the standard error is going to be the square root of p hat times q hat, which is 1 minus p hat over n. And for a sample mean, it will be s over square root of n. Recall that the sampling distribution model of p hat is centered at p with standard deviation square root of p times q over n. If we don't know p, we can't find the true standard deviation of the sampling distribution model, so we're going to use that standard error. Let's look at the 68, 95, 99.7 rule. So in particular for sample proportions, we're going to find that about 68% of the data are going to fall within one standard error of our proportion p, and within two standard errors of our proportion p, we're going to capture 95% of the data, and then 99.7% of the data will be within three standard errors of the true proportion. All right, this we know. What we're going to do is we're going to shift our view and look at it from the sample proportions point of view. Since there is a 95% chance that our sample proportion is within two standard errors from p, there's a 95% chance that p is no more than two standard errors away from the sample proportion. So if we reach out two standard errors, we are 95% sure that p will be in that interval. In other words, if we reach out two standard errors in either direction of p hat, our sample proportion, we can be 95% confident that this interval contains the true proportion. This is what is called a 95% confidence interval. So here's a little picture here just to help you see what it looks like from the point of view of our estimate. Here's the estimate that we get, our p hat. If we subtract two standard errors from it and add two standard errors to it, it's reasonable that we can have 95% confidence that we've captured the true proportion. Okay, so let's talk about what 95% confidence really means. Each possible confidence interval uses a sample statistic, in this case, p hat, to estimate a population parameter, in this case, the population proportion, so p. But since samples vary, the statistics we use and thus the confidence intervals we construct vary as well. We've already kind of talked about that. We get that p hat has a sampling distribution, so that means there is a distribution of confidence intervals as well. The figure to the right shows that some of our confidence intervals from 20 random samples capture the true proportion, which is represented by this green line, while others do not. So the red dot on here, on each one, represents the sample proportion, the p hats. And then we've got are whole confidence intervals. Um, these are, which we'll talk about formally in a minute, but you've got your estimate and then it goes out your margin of error in one direction, margin of error in the other direction. So if you look, most of these intervals capture the true proportion. There's a couple that don't, but we expect that in repeated sampling. Anytime somebody's asking you to explain what 95% confidence means, they're asking you to say, okay, in repeated sampling, what happens? Um, if they ask you to interpret a particular interval, that's something else. Our confidence is in the process of constructing the interval, not in any one interval itself. Thus, in repeated sampling using the same methods, we expect 95% of all such intervals to contain the true parameter that we are estimating. We can claim with 95% confidence that the interval p hat plus or minus 2 times the standard error of p hat contains the true population proportion. The extent of the interval on either side of p hat is called the margin of error and is abbreviated ME. In general, confidence intervals have the form estimate plus or minus the margin of error. The more confident we want to be, the larger our margin of error needs to be, making the interval wider. So we're going to be wrong less of the time because our interval is going to cover more possibilities. To be more confident, we wind up being less precise. We need more values in our confidence interval to be more certain. The problem is an interval can become too large to be useful. It's, um, so here, it's showing you one that is 3 standard deviations below the mean, 3 standard errors above the mean. And yeah, we can say with 99.7% confidence, but that doesn't really help us narrow down what to expect. Okay. Somebody can say, yes, we predict that a certain candidate will get between 0% and 100% of the vote and be really, really confident that that's true, but you've lost so much precision, it's a meaningless interval. It doesn't give you any new information. So sometimes people ask what's the best confidence level because you can pick how confident you want to be. It depends on the situation. Every confidence interval is a balance between certainty and precision. Fortunately, in most cases, we can be sufficiently certain and sufficiently precise to make useful statements. The most commonly chosen confidence levels are 90%, 95%, and 99%, but any percentage can be used. The 2 in the p hat plus or minus 2 standard error from for our confidence interval came from the 68, 95, 99.7. Using a table or technology, we find that a more exact value for our 95 confidence interval is 1.96 instead of 2. We call 1.96 the critical value and denote it as Z star. It's our little star. For any confidence level, we can find the corresponding critical value, the number of standard errors that corresponds to our confidence level. So, for example, a 90% confidence interval has a critical value of 1.645. Okay, now we do have to check assumptions or make assumptions and check conditions for a confidence interval for a proportion. All right. Our assumptions are independence assumption and then a sample size assumption that it's large enough. We first need to think about whether the independence assumption is plausible. It's not one you can check by looking at the data. Instead, we have to check 2 conditions to decide whether independence is reasonable. The first one is the randomization condition. Were the data sampled at random or generated from a properly randomized experiment? That's what you want to be able to say yes to. Proper randomization can help ensure independence. And then the 10% condition is the sample size no more than 10% of the population. The reason this is important is because if we don't have independence, technically the probability of success changes after each observation is made. But if our sample size is less than 10% of the whole population, that's not going to affect our calculations to a point that it causes a problem. We can go ahead and act as though the observations are independent. All right, so sample size assumption. Okay, we just made sure it wasn't too big to cause a problem. Now we want to make sure it's large enough for us to be able to use the central limit theorem. So we check the success failure condition. We must expect at least 10 successes and at least 10 failures. Okay, so a one proportion Z interval. When the conditions are met, we are ready to find the confidence interval for the population proportion P. The confidence interval is P hat plus or minus Z star times the standard error of P hat, which is the square root of P hat times Q hat over N. And Z star times the standard error of P hat, that is the margin of error. The critical value Z star depends on the particular confidence level C that you specify. And here we have the Z stars for several confidence levels. The question of how large a sample to take is an incredibly important step in planning any study. Choose a margin of error and a confidence interval level. You want to know how confident you want to be and how precise you want to be. The formula requires P hat, which we don't have yet, because you need to know how many observations to make the observations and calculate the P hat. But so a good estimate for P hat, which will actually yield the largest value of P hat times Q hat, and therefore N, is 0.50. So we want to solve the new formula for N, and we're always going to round up. So our margin of error is Z star times the square root of P hat times Q hat over N. So if you do the algebra, you'll see that N equals Z star squared times P hat times Q hat over ME squared. I usually just go ahead and plug in the values in the untransformed formula because that one, anyway, that way I don't have to memorize another formula for N, and then just do the algebra then. Okay, if you want a smaller margin of error, you have two options. One way to make the margin of error smaller is to reduce your level of confidence, but that may not be a useful solution. You may need a certain level of confidence. The second one is to use a larger sample, increase N. To get a narrower interval without giving up confidence, you need to have less variability. Increasing N does this without lowering confidence. So why don't people just keep increasing N? Remember, we don't want to go above 10% of our population, and sometimes it's expensive. Sometimes your budget will only allow for a certain sample size, and so that's just kind of a real world limitation that people have when they're conducting surveys. All right, let's look at some examples. A May 2000 Gallup poll found that 38% of a random sample of 1,012 adults said they believe in ghosts. Find the margin of error for this poll if we want a 90% confidence in our estimate of the percent of American adults who believe in ghosts. All right, so we are going to plug in our values. All right, we're looking for the margin of error here. We know what N is, so this is a little different than the last thing that we talked about so far. So don't let that confuse you. So we're looking for the margin of error. Our critical value, because it's 90%, is 1.64, which you can get from the table with the values for the t-distributions, or you can use inverse normal area to the left with your CAS. That's going to be the 1.64 times the square root. We actually have the sample proportion, so 0.38 times q hat. That's always 1 minus p hat, so 0.62 over 1012. And so we get 0.025, which is 2.5%. Explain what the margin of error means. The pollsters are 90% confident that the true proportion of adults who will say they believe in ghosts falls within 2.5% of the estimated proportion, 38%. If we want to be 99% confident, will the margin of error be larger or smaller? Explain. It's going to be larger. When everything else is held constant, to gain confidence, we lose precision, which means we will have a wider interval. Let's test our answer to part C by finding the margin of error for 99%. All right, the only thing that's going to change is our Z star. So with 99% confidence, our Z star is 2.56. The standard error is the same. So we do our standard error times our Z star, and we get 0.039, and we get 3.9%, which is larger. In general, if all other aspects of the situation remain the same, will smaller margins of error involve greater or lesser confidence? Okay, if we reduce our margin of error, we are reducing our precision. We are increasing our precision as we reduce our margin of error. And so we are lowering our confidence. We will be less confident, but more precise. All right. In a survey of 226 randomly selected college students, 20 reported being only children with no siblings. Estimate the proportion of students nationwide who are only children. First, we need to check the conditions to the extent that we can for constructing a confidence interval. It's likely that each student's sibling status is independent from another. The sample was randomly selected, and there are more than 10 times 2,260 college freshmen. There were 20 successes and 206 failures, both of which are greater than 10. We want to construct a 95% confidence interval. This time, we're going to just use the CAS. Okay, you're going to go to your scratch pad, and you're going to go to statistics, and you are going to then have the menu where you've got all kinds of things. We want to construct a confidence interval, so we're going to select confidence interval, and we want a 1 proportion Z interval. The two at the top, the Z interval, T interval at the top, those are for means. And so we don't want to use those. We want to use the things that say proportion. Once you do that, you're going to have a menu, and you're going to be prompted to put in the number of successes. So that was 20. The sample size, so 226, and your confidence level, which is 0.95. And then you click OK, and then boom, the CAS gives you everything you need. It reminds you of what kind of interval you just created, and it's going to give you the lower end of your confidence interval and the upper end of your confidence interval. It even reminds you of what the sample proportion is. It tells you what the margin of error is and what N is. So our confidence interval is 0.051 to 0.126, or 5.1% to 12.6%. We want to interpret our interval. So this, when it says interpret your interval, we're interpreting the particular interval we just created. So what does 5.1% to 12.6%, what does that mean? We are 95% confident, based on this sample, that the true percentage of all students who are only children is between 5.1% and 12.6%. Explain what 95% confidence means in this context. Okay, remember, anytime they ask you to explain what the phrase, such and such percent confidence means, it means something about the process and doing the process over and over. So, continuing to use the same methods and repeated sampling, 95% of all such random samples would produce intervals that would contain the true percentage. And now we're going to put in our context of college students who are only children. All right, now we're going to change scenarios. A state's environmental agency worries that many cars may be violating clean air emission standards. The agency hopes to check a sample of vehicles in order to estimate the percentage with a margin of error of 3% and 90% confidence. To gauge the size of the problem, the agency first picks 60 cars and finds 9 with faulty emission systems. How many should be sampled for a full investigation? Okay, because they did the pilot study, we have an estimate of what p hat is. If they had not done the pilot study, we would have used zero point 0.5 for p hat. But they did the pilot study, and so we have a rough estimate of 9 out of 60, so 0.15. So we're going to use our margin of error formula. They want a 3% margin of error, so we're going to have 0.03. They want 90% confidence, so the critical value for 90% is 1.64. And we're going to do the square root of our best estimate so far, the 0.15, and then we'll find Q hat, which is 0.85, over N, which is what we're looking for. All right, so right now, the N is in a denominator in an expression that's being square rooted. So we're going to undo the square root first by squaring both sides. Now, guys, I tend to wait to do the calculation to the very end so that I'm not tempted to round as I go. So 0.03 divided by 1.64 squared is equal to 0.15 times 0.85. All right. At this point, you can multiply both sides by n or cross multiply, whichever way you want to do it. And so we're going to have our squared term times n equals 0.15 times 0.85. So we need to divide both sides by this value that n is being multiplied by, our squared value. And so we're going to get n equals, and luckily for our with our CASs, it's super easy. Well, maybe not super easy, but it's somewhat, doable to put all of this in all at once. So we're going to put in our expression 0.15 times 0.85 divided by 0.03 over 1.64 squared, and we get 381.012667. Now, if we were rounding, we'd put 381, but we're not going to round. We're always going to go up to the next value for n if there's any fraction over to the side. Okay, and that's because you want a specific margin of error. And if we did 381, it would be a tiny bit larger. So we're going to do 382. Okay, guys, that's it for this video. Thank you so much for your attention and for watching it. If you have any burning questions, feel free to ask me. Just come by or send me an email. Go ahead and do the problem to try on your own, and then we will go over that in class. Thank you so much. Have a great day.